third lecture.
All right. Good morning.
Did you start recording?
So remember what we did last time. We started talking about this proposal that unitary topological quantum field theories in general dimension have partition functions which are homomorphisms from the Bordism group of manifolds in the dimensions to U1. And we started discussing some examples of computing this Bordism group and trying to match against known results in the literature. So I'll give a few more examples just to try to convince you that this works, and then I'll discuss where this conjecture comes from. And in fact, it's essentially by this point it's essentially a theorem that invertible unitary QFTs are described by Bordism like this. All right, so a few more examples. So remember, the examples we discussed last time were bosons without symmetry, in 1 plus 1D. Here the classification is trivial. Z1 fermions. Without symmetry in 1 plus 1D. We have the Z2 classification where the generator assigns to the torus with Ramon boundary condition -1 and the generator of the homomorphism. And this was the Kitaev phase. Kitaev chain, and well, because if you take the square of the partition function, you get 1, so it's a Z2 phase. Now, what about adding some symmetry? So let's say we have time reversal symmetry.
Sorry, Max. Before you go on, you said here that okay. So last time, did you explain why? So we saw that if Z is for this invariant, then it has some properties. But did you explain why the invertible phases are for this invariant?
I'm going to talk about that. Yeah, I'm going to talk about that later. So.
Okay. So for the moment, we don't know that the invertible unitary QFTs
have Bordism invariant partition functions. That's right. Okay, so how? Let's discuss time reversal symmetry. Now, if you have time reversal symmetry, it allows you to put the theory on a non-orientable manifold. Right? You can have transition functions between different patches that reverse orientation. You know how to transform your fields. And so then the natural thing is to consider TQFTs, to consider your theory on non-orientable manifolds. So the Bordism group that we should consider then is the unoriented Bordism group, one that allows for unorientable manifolds. Symmetry. So this is known as omega O of whatever dimension. So let's say in 1 plus 1D. And this group turns out to be Z2. And its generator is the real projective plane RP2. So that's the sphere with opposite points identified. Again, there is one non-trivial phase that assigns to RP2 -1. So this is so again we have a Z2 classification for such time reversal invariant boson SPT phases, invertible boson phases in 1 plus 1D, and this can be proven actually on the lattice. In one dimension you have a lot of, in 1 plus 1 dimension you have a lot of power on the lattice for gap phases, and you can actually prove that this is the only, that this is the right classification. This is known as the Falden chain, actually. There is a very simple physical model that realizes this, which is a antiferromagnetic spin 1 chain. Known as the Falden chain, and here the time reversal acts by in the way that it actually acts physically.
As far as I know, it has not been proven that this Falden chain is even gap. So when you say proved on the lattice, it means assuming.
No. What I said proved on the lattice is that you can prove on the lattice that all time reversals, that there are two time reversal invariant boson SPT phases, trivial and non-trivial. So for this particular model, in fact, it has not been proved that you have a gap, but numerically we know, without any doubt, that this phase belongs, that this Hamiltonian belongs to this non-trivial phase. All right. What about fermions with time reversal? So for fermions, it's natural. There are two natural time reversal symmetries.
Can I ask you a question about this Falden? So you're saying that if you don't impose T-symmetry, then it's actually it can be trivialized?
Yeah. If you don't impose any symmetry.
Yeah, if you don't impose any symmetry.
That's right. It's not. Not so surprising. If you think about the edge
Because it has the general ground state, nearly the ground state.
on a chair, on an open chair.
Yeah, an open chain.
But you can, if you break the symmetry, you can lift the degenerates. If you break spin rotation and time reversal, then you can lift the degenerates. All right. For fermions, there are two natural actions that time reversal can have. Time reversal can square either to 1 or to -1 to the fermion parity. And when you put such theories on curved manifolds, particularly on non-orientable curved manifolds, there are the structures on the manifolds that you get are so-called pin plus and pin minus manifolds, just determined by when you lift your element of OD, the Euclidean rotation and reflection group 2. It's double covered. There are two kinds of double covers you can have depending on what the elements that reverse orientation square to, and these are so-called pin plus minus D. So for T squared equal +1 in Minkowski space, the right structure is actually pin minus. So let's say we compute Bordian group manifolds with these pin minus structures in 2 dimensions. What you get is ZA, which is generated by.
Sorry, could you repeat? Well, how do we know it's pin minus and not pin plus?
If in Minkowski space T squared equal +1, then in Euclidean space you will find that t squared equal minus 1. And that's the pin minus structure when you analytically continue. And
That means that there's no physical significance to the pin plus, or
the
that cannot be
pin
continued
plus
by two.
corresponds to t squared equal minus 1. Minus 1 to the f. So t squared.
But is it a choice, or am I supposed to choose one based on the something?
Oh, whether t squared is plus 1 or minus 1 to the f?
Yeah.
So that's your microscopic model, right? You have some microscopic model that has some symmetry.
Okay.
If the symmetry is like this, then you study pin minus structure. If it's like this, you study pin plus structure. So it's just different symmetry classes.
And both are realized in
Well, in our nature, this happens. But in some effective law, in some effective model, you might end up with time reversal that acts like this. This might be the physical time reversal combined with some extra operation. So the generator of this Bordism group is RP2, and then the generating homomorphism is one that assigns to RP2 the eighth root of unity. Right? So and then in the general homomorphism assigns to RP2 2 pi I over 8 times k, where k is an integer modulo 8. Right? So we get this eightfold classification. Now again, for this fermions in 1 plus 1 dimension, one can derive the exact classification on the lattice, and it agrees. It's actually very beautiful. So the generator of this Z8 on the lattice is the Kitaev chain that I talked about, enriched with time reversal, where you just make the electrons, the fermions Ci go to Ci and the time reversal. And without interactions, turns out that the classification, if you just consider free fermion chains with that symmetry, you find that the classification is Z. Any number of chains is a separate topological phase. However, with interactions, the Z breaks is reduced to Z8, eight copies of the Kitaev chain can be continuously connected to a product state if you allow for interactions. This was shown by Titkovsky and Kitaev back in 2011, and this classification correctly captures this Z8. So one question that a few of you have asked is, is this just for free fermion phases? And the answer is no. This is for arbitrary interacting TQFTs. It doesn't have to be free fermion. Okay, so this is quite a non-trivial example. Another famous example is fermions in 3 plus 1 D with t squared equal minus 1 to the f. So like I said, in this case, you should compute the pin plus Bordism of infrared cutoff. And this Bordism group turns out to be D16 generated by RP4. So you assign the generator of the classification, then again the classification is Z16. The generator assigns the 16th root of unity to RP4. Again, the non-interacting classification in this case is integers, and interactions break this to Z16. And there have been, in this case there is no proof on the lattice that this is the case, but there have been very plausible physical arguments that you get this Z16 and it agrees with the Bordism calculation. So hopefully, now in all of these examples, in all of these fermion examples,
And do we have a physical model here that realizes this?
well, the generator again is a pre-fermion.
Oh,
Is a pre-fermion phase, and actually this generator is believed to be helium-3b. It's believed to be realized in helium-3b, where it's a superfluid of helium-3, which is well, apart from the Goldstone mode, is gapped in the bulk, and on the boundary it realizes a single Majorana hole. So this is the boundary of the K=1 phase.
So what's the claim? That there is some very simple free fermion Hamiltonian involving 16 pieces of the fermion, to which you should be able to add an interaction which gaps it.
That's right.
But this has not been, this is difficult to check that this interaction gaps the fermion. Why is it so difficult to show this?
Well, let me try to say exactly what has been done. So first of all, in the bulk, it's very difficult to show a continuous path. On the boundary,
No, but why can't you just have, you said, it's an easier result. You said Kitkovsky and Kitaev proved that 8 copies of Kitaev chain can be gapped. Very interesting introduction.
That's right.
Interaction.
That's right.
So,
The way they showed it is that you start with 8 copies of the Kitaev chain.
yeah.
There is a transition from the trivial phase to the so first of all you can look at the edge, right? On the edge, each one first contributes a Majorana mode gamma. All of these Majorana modes transform in the same way. Once you have 8 Majorana modes, you can show that you can write down a 4 Majorana interaction that gets them up. So that's already kind of an indication. Now what about in the bulk? So in the bulk, they were also able to show a path. So remember, there is this transition between the trivial chain and the Kitaev chain, which is just a gapless Majorana. So now you can look at this theory of 8 gapless Majoranas, and you can write down certain 4 Majorana interactions, and you can argue using certain triality relations of CFT that you have that essentially you have this in free fermion theory you have this gapless point, and that you can go around. But this relies on knowing something about 1+1 DCFTs, so it's some work. That's one way it's been done. There is another way you can actually do this, which you don't look near this gapless point, but you do something similar, I think, to what we did with a single. With 2 copies of Kitaev chain without time reversal, which was, we could show that for each one of these blocks, we can continuously connect to this, and then we continuously connect to this. So for 8 copies with Majoranas, with time reversal, I can do the same. So in that case, it's easier. But in 3+1 dimension, even on the boundary, it's complicated because you have this Majorana mode, and you have to write down some interactions that would, you have this 16 Majorana cones, you have to write down some interactions that would drive them into a trivial phase. One way that has been done is with you couple it to some, you couple these 16 Majorana cones to some bosonic field, and you integrate that will break the symmetry. You integrate the Majorana cones out, you get some kind of nonlinear sigma model. And then you have to argue that this nonlinear sigma model doesn't have any topological terms like the Vazumina-Witten terms. And for 16 copies, you can show that. There are other ways it has been shown too. We can discuss.
And what's the envelope of C equal 1/2 in 3+1 dimensions? So you had access to C equal 1/2 theory. And
Yeah. So here it's in the bulk.
yeah, in the bulk.
In the
there
bulk,
some
it's a gapless 3+1 dimensional Majorana. So
That's free theory.
free
Okay,
theory.
that's
Free
good.
theory. Other questions?
So in the earlier example of the Haldane chain, can you say what's the significance of the spin 1?
It's just that for this particular model, spin 1/2 chain is gapless. And spin 2 turns out to be in the trivial phase. So it turns out to be odd spin odd integer spin ones that realize the Haldane phase. Other questions? All right. So this.
Max.
Yeah.
So the integer k indicates the number of copies of your fermions that you have, right? So that indicates, I guess, the maximal kind of flavor symmetry. So, but you said the flavor symmetry has to be broken to make this Kita chain.
So here I'm not imposing flavor symmetry. I could impose, in addition to time reversal, I could impose, I don't know, SO16 flavor symmetry, and the classification would be different in that case, I believe. I have to remind myself, but I think the classification would be different. You would have some kind of theta term for SO16 in the bulk with theta equal 5, presumably. I'm guessing at this point. Yes?
RP2 is unorientable. Right?
That's right.
Does it make sense to ask about bosons with T-symmetry on orientable methods?
Yeah. It's just that we know that without any symmetry, there is no non-trivial phase of bosons in 1+1D. So you don't expect anything. In fact, the partition function of this is on the general manifold is -1 to W1 squared, where W1 is the first Diffie-Whitney class. It just measures your orientation reversal. So if you are on an oriented manifold, W1 is equal to 0, and this is trivial. More questions? All right, so this seems to work, but why? And here is the, well, in my discussion it will be an argument, but it can be made into a proof. Z of mg is a Born invariant. Assuming that, well, assuming we have topological quantum field theory, right? So the partition function does not depend on the metric. And dimension of Hilbert space on any d-1 dimensional manifold is equal to 1. In fact, I think you need less than this. You need only dimension on certain particular manifolds to be equal to 1, but let's assume this. Remember, this was our discussion of invertibility. The Hilbert space on a special manifold has to be one, has to have dimension 1. So this is of course the ground state, Hilbert space. So this is a theorem by Dennet-Fried and Craig Moore. And there's been a more recent work by Yonekura that incorporates symmetries into this theorem. And the idea is the following. Right, so this is answering the question that many of you have been asking: why Bordism? The idea is about cutting and gluing. Suppose you have some borders. Any bordism can be decomposed into sequences of so-called elementary bordism. The elementary bordisms are between manifolds M and M prime, where M prime is constructed from M via surgery. More precisely, what you do is you start with M, some manifold, and you cut out from M the following open set. Sphere times a disk. In the case when P is equal to 0, you're just cutting out 2 balls. Right, as 0 is just 2 points, so you're cutting out 2 d-dimensional balls. And then the way you construct M prime is you glue in D equals 1 cross SD minus P minus 1. So the boundary of this, well, let's consider the boundaries, right? What you cut out here has a boundary SP cross SD minus P minus 1, and this has the same boundary SP cross SD minus P minus 1. So you just glue this thing in along the boundary that you obtained after the cutting out. So basically, you, in the P equals 0 example, you just attach a thing like this. So you get the manifold M prime in this way. And turns out that all Bordisms can be decomposed into such elementary Bordisms where the initial and final states of the Bordism are this kind of surgery.
But it's not obvious that M and M prime is a Bordism.
That there is a Bordism between these two. It is actually quite simple to show. Let me see if I can remember. I think you take. I'm not sure I'll get it right, but I think you get MD. You start with MD cross I, then you glue to it
I is an interval here.
Anyway,
in an interval union
only if it's important, I don't
D
think.
equals 1. And you glue at the top of the interval. Yeah, let me not try to do this. Let me draw a picture here. Maybe it will
Yeah, maybe.
make sense. So what am I doing? Let's start with the M, which is top here. And let's do the P equals 0 case.
So I thought the top manifold is the union of two circles.
Yeah, let's do it the other way around. Doesn't matter. Right. So let's start. This is M. This is M prime. I take my two circles. I cut out. So P equals 0 case. I cut out S0 cross D1, so cross an interval. So I cut out two intervals. So I start with this, cut them out. And I want to glue back in. What was it? I just erased it. D P plus 1 cross S D minus P minus 1. So in this case, it will be an interval cross S naught. So I put glue in.
Yeah, that's exactly the picture. Okay. Okay, thanks.
I guess you can define a Morse function so that the P is the Morse index.
That's exactly how this decomposition into elementary Bordism was proven. All right. So now we want to show that under such surgery operations, the partition function remains the same. That the partition function of MD and M prime D is the same. Then we prove Bordism invariance of partition function. All right. So let's think about this. If you have a manifold, arbitrary manifold, and you glue it from two pieces, first of all, if you have a manifold with a boundary, then in Tk of t, you should think of that as a state in the Hilbert space on the boundary of that manifold. Well, in fact, that's true not only in Tk of t, but in the Tk of t it will be a ground state. So this is a state in the boundary of your manifold. And when you glue, you should think that as an inner product of two states. So there is a state phi, there is a state psi, and then the partition function of this on this manifold should be called as the inner product of this. Okay, so let's see. The partition function of my initial manifold M before surgery I can think of as the inner product of the state prepared by the manifold with this cut out, inner product just with the state prepared by the manifold that I cut out. Right, so in this particular case, in the p equals 0 case, this is the bra, this is the cat. Similarly, z of m prime is the inner product of this with whatever state is prepared by the thing that I glue in. Right, so this is prepared by the tube that I glue in. Very good. Now, we are assuming that the ground state of our theory on any d-1-dimensional manifold is unique. Right? So all of these states that I have here are just the same up to a constant proportionality factor, up to a complex proportionality factor. So in particular, let's say here, in Z of M, I can insert
Max, sorry.
this state.
Did you, so we, I don't remember very well, but when you introduced invertible phases, you said that indeed test to have a unique ground state, but why for different manifolds the vectors be the same up to a constant? Like with the
No, but these are the same.
so these are.
These are, I cut, remember I said that the boundaries are
sorry,
actually
yeah,
the
so
same,
left
and you
one is
cut,
the same.
cut in along the
Sorry.
same boundary. Cross. So I'm just going to insert this state here, dp plus 1 p minus 1 plus 1, and then I put my and I divide by the norm squared of this state. Okay, what are the resulting partition functions that I get? This is the partition function of m prime. What is this? You could glue dp plus 1 cross sd minus p minus 1 and sp cross dd minus p. So you just glue this to this. What is the resulting manifold?
SD.
SD. And here just the norm of this state will be the manifold that I get by gluing is S p plus 1 cross SD minus p minus 1. So I get the relation between the partition functions on M and M prime that involves some extra factors of partition functions on products of spheres. Now, turns out that these factors essentially end up being 1. So we have to, let's begin with this partition function of a d-dimensional sphere. We can show that if d is odd, this partition function is actually equal to 1 using the same cutting and gluing argument.
Sorry, Max. In the picture, the first z of SD is clear, but the second one, if I join these two tubes, why don't I get a torus? If I put, I'm just looking at the picture and imagining that I put a cylinder like that, and then I put one below. That's a torus, of course. Yeah, I'm sleepy. Okay, good. Okay.
Other questions? Yes?
Yeah, so when you cut a TQ of T and get a boundary, why is it just one state? I thought, okay, for example, the KTI chain in a non-trivial phase, and you cut the boundary open, and you get 2 states, right?
This is a little bit different. You're thinking about the wave function that you get. So, right? Imagine we have this. Oh, let's go. You're doing a path integral, right? And let's say you fix the value of the fields on the boundary.
Okay.
I don't know how to call them. I already called this phi. Let's call the fields x. And you're doing the path integral over the rest of the fields in the bulk.
Yeah.
So this gives you a wave function psi of x.
Yeah.
Z on this with a fixed boundary x gives you psi of x.
Okay.
So this is how you should think of this as a state in the Hilbert space on the cut.
Okay.
And then, of course, when you glue with something,
Yeah.
right, then you have x, you have x prime, and then you have to identify x and x prime and do a integral over this x. So that's exactly the inner product of the two wave functions.
Okay.
And then if you have a topological field theory, then you can essentially this boundary you can extend this tube as much as you like, and that projects, you can think of this as time evolution, and this projects out the ground state. And here we're assuming that the ground state subspace on any manifold is non-degenerate.
Yeah, so when you write this down, you do have to sum over the boundary conditions, right? So x and x prime, when you glue them. Right.
Well, you have to take the inner product of the two wave functions that you get, but these wave functions are the same up to a constant because we are assuming that that the ground state manifold is non-degenerate. I think your question is, how are the edge modes of a Majorana chain connected to this wave function? So it's a different interpretation.
Okay, I'll have to think about it. So thanks.
And the wave function is not a ordinary boundary, it's not a local boundary condition. It's just a function of the degree of freedom on the boundary. That's not the same as a local boundary condition.
Okay.
It's a bit confusing because now you just seem to be doing one-dimensional linearity.
Yeah.
But you project onto the ground state, but you want to keep the phases, I guess, because otherwise there's nothing left to do.
That's right, but we do want to keep the phases, but you see the phases cancel out.
Uh-huh. I see.
So this, in the d-dimensional case, when d is odd, you can, using the same, essentially the same operations, you can show that the partition function is equal to 1.
But isn't this the same? You were saying that the reflection positivity, if we can glue the manifold to things which have opposite orientation.
It has to be positive, for sure. Why 1?
But you always were saying that all these things are one.
No. I will come
They
to.
were just, you said they were pure phases at the very beginning.
I will come. So I'm trying to prove now some of this, right?
Are these sets pure phases?
Well, we saw that under the Bordism assumption, and together with unitarity, they're pure phases. But now I'm trying to prove Bordism, that the partition function is a Bordism invariant. In the even D case, you're not assured that the partition function on SD is 1, but you can always make it 1 by local counter terms. Because in the even D case, you always have...
Can you give what D case, because it's becoming very confusing.
Sorry?
You started your lectures by saying you can always add local counter terms that the partition function is pure phase. You started your lectures by saying that basically.
Yeah.
Now you are no longer sure that that can be done?
I'm trying to prove that fact.
From what assumptions?
Unitarity and TQ and locality, cutting and doing.
Invertibility, it's important that.
Right, so I'm proving Bordism. I'm proving that for a TQ of T, where the ground state on any spatial manifold is non-degenerate, the partition function is a Bordism invariant. From that, together with unitarity, the fact that the unitarity and, well, actually, reflection positivity, it follows that the partition function is a pure phase. Remember, we showed that last time.
Don't remember, because I didn't realize that this needed to be shown, because you said that it's obvious.
Right, so that is a map from Bordism group to initially complex numbers. So as long as it's Bordism invariant, right? So now Z of x times Z of x bar
X bar is the inverse of X.
is the x with opposite orientation, has to be equal to 1. Now Z of x bar is the complex conjugate of Z of x by unitarity, so Z times Z star is 1. But the assumption here is that the partition function is Bordism invariant. So I'm trying to prove Bordism invariant.
Okay.
And I claim that for odd D, I can use the same cutting and gluing to show that the partition function of the sphere is 1.
Can we consider case d equal 1 for these two?
Well, d equal 1 is trivial, right? Because z of S1 is just the dimension of the Hilbert space on the point. But let's do z of S3.
Okay.
Z of S3. I decompose S3 into D2 cross. Let me make sure I get it right. D2 cross S1 union S1 cross D2. So this is
Now you do the trick.
now. How do I do this? So this is some phi. This is some chi. I know this has to be positive by reflection positivity. So z of S3 squared has to be equal to phi times chi. And because this, these are the same state up to a complex number, and this is partition function on S2 cross S1 times partition function on S1 cross S2. Both are equal to 1 because the Hilbert space on S2 is one dimensional. If I did S4 in the same way, I could, so for even dimensional G, the partition function does not have to be on entity doesn't have to be 1 because I can have a partition function like this, e to the alpha chi, where chi is the Euler number on the manifold, right? So for a sphere, Euler number is equal to 2.
And alpha is real.
And alpha is real.
Okay.
This is a perfectly this is a perfectly okay unitary TP of T. But of course, I can get rid of this. I can always add a counter term like this in order to make Z of S equal to 1 for D even. And then, once we have Z of S equal 1 for D even, we can actually, using same ideas, also show that this partition function on products of spheres is equal to 1. So then the partition function is a Bordian invariant. So that's the theory.
Sorry, I'm still a bit confused about the phases. So here you have a half-erased picture where on the right board, the other right.
I don't know.
Yes, so where Z of this manifold is phi inner product psi, right?
Yeah.
But why is it phi inner product psi, but why not psi inner product phi? I mean, I take a manifold, I cut it into pieces, what determines?
There is some orientation that you have to specify.
But, so what do you do in practice?
There has to be an in, right? One of them is,
But Z of a manifold,
that's right.
right?
The orientations have to combine so that you get something smooth on when you glue together.
But I have a manifold with orientation, I cut it in two, but
So there's an orientation associated with a d-1 dimensional submanifold on which you cut.
yes.
That orientation, you pick one. If you pick the opposite orientation, that will go right away from
You get the opposite. Okay. because that manifold must be 5 psi.
Given already manifold with boundaries in the left half, right? There's a canonical orientation associated with the boundary.
Yes.
You don't have to flip it once you have picked the orientation on the whole thing. So the whole manifold, you pick the orientation, right? That's the Barring function. If you have sort of the opposite orientation, Barring function gets funded. I mean, it's consistent. So once you have picked this orientation, you don't get to change the orientation boundary anymore. So there's one. So the other side, you will have the opposite. The boundary will have opposite orientation, but in order to match, you have to flip that. So that tells you whether it's a ket or not.
So sorry, so this means like I can use, in that picture I can use like rank and rule to establish if the manifold is on the left or on the right of the boundary, and that defines for me what is the ket and what is the bra. That's what you're saying. I choose a circle there, and then I say if the manifold is along my thumb, then that's the ket. If the manifold is on the other side, that's the bra.
I mean, one could say that on the left side there's a boundary, on the right side there's another boundary. If you choose the left and the right side, the bulk to have the canonical orientation you started with, then the two boundaries will have opposite orientation, right? So in order to glue, you have to flip one in order to match them, and you have to choose whether to flip which one to flip.
All right. So let's see. So we are done, I think, with this part. Now, let's come back to the low dimensional. Yeah.
Can I ask one more question about unitarity? So this unitarity here seems to be, I don't know, is it stronger than the unitarity that we normally? It seems to be stronger than the unitarity that we normally require for, say, non-topological quantum field theory, in the sense that it affects completely local terms. This, if alpha was complex, we wouldn't see it in any local correlation functions. For instance, if we had a quantum field theory, is that correct?
That's correct, but you would see it in more partition function on a torus. Actually, you will not see it.
Yeah, every time it's in local operators.
You only see it on a sphere.
So all the CFT data or quantum field theory data, local quantum field theory data is blind to this.
Well, let's see. So let's say 2D CFT, right? That the partition function on a sphere has the central charge in it, but
yeah, but that's
the central charge is real.
So this is because this chi is linked to another piece which is non-local. This is R1 over box R, and both of them have the central charge. So then it appears in the two-point function of the stress tensor, for instance, through there. So okay, so I guess something goes wrong if I try to take those two partitions different.
You're saying what happens? Can I make a non-unitary invertible TQ of T if I make alpha complex?
Yeah.
I don't know. Off the top of my head. Okay, so one thing I want to discuss is, now that we've proven Born invariance, let's discuss these homomorphisms from Born group to U1. So the Born group in general is some kind of, well, it's an abelian group. It's a bunch of direct sum of some torsion pieces and a bunch of free pieces. If I consider the homomorphisms from these torsion pieces to U1, of course, the homomorphisms send 1 to the nth root of.
Sorry, Max, I was still trying to digest that there. So when you wrote z square, it was, you would write normally z times z star, but because you argue that z is real by reflection positivity, you write z squared, right?
That's right.
Okay.
So these torsion pieces in the Borgian group give me the same torsion pieces in the group of homomorphisms. So they just come through. What about the z pieces? What are homomorphisms from z to u1y? I send 1 to e to the I theta, where theta is the phase. But now, this theta is not a discrete quantity. I can tune theta. So this actually doesn't give me, the different colors of theta do not give me different phases, because I can tune continuously between them. So it's only the torsion part, it seems like it's only the torsion part of omega d that gives you TQFTs. So invertible TQFTs. So invertible.
But actually all the Borgian groups that we wrote so far, they didn't have the Z piece. They only had
The simplest one that does, I think, omega 4 as O is equal to Z. And this one is generated by CP2, and the Borgian invariant, the integer Borgian invariant is the signature. Okay, but when I wrote down the invertible phases in low dimensions, I had some z's appearing in that. This is saying that I only get torsions. I only get finite groups. But let me remind you of the classification I wrote down in one of the first lectures.
Sorry, in that example you wrote, you said the Borgian group is Z, and then you said only the torsion part contributes, so there's no phases there?
That's right, it would seem.
But you just said there is phases, or?
So let me.
Okay.
Invertible phases. This is the table I gave in one of the previous lectures. The dimension 1 plus 1. And for bosons, this was trivial, but this was still z. So there are some z's appearing here. So where do those z's come from? Well, turns out that these z's come from invertible phases whose partition function is not metric independent.
It's not metric independent.
It's not metric independent. So strictly speaking, they are not topological quantum field theory. Their partition function depends on the metric.
I will change the rules.
But this metric dependence is very mild. And in fact, so let's discuss this example.
Actually, can I ask? So there's mathematical theorem, pretty Hopkins,
Yeah.
I guess, that says that you can every Borgian invariant given by this Sperry function corresponds to this some polynomial field theory, you can reconstruct polynomial field theory. That, are you saying that only refers to these torsion parts?
No, they also put in these ones that depend on the metric, but
Oh, I see.
but that is so I'll come to that. So what about this P plus IP superconductor? Well, you can actually model it by
So I'm confused another. Isn't omega 2 trivial? Sorry, I'm confused. So where does the 2 come from?
no, it depends on whether you're thinking about bosons or fermions. For bosons it's trivial, for fermions it is omega 2 spin, it's Z2. That was the torus with Ramon spin script.
Okay, so that's fermions.
So you can model the P plus IP superconductor as a gapped Majorana fermion with an inverted mass. Again, if you think about the domain wall where the sign of the mass changes, then you get a chiral 1 plus 1d Majorana on the boundary. And you can compute the partition function of this on a closed manifold using the same technology we discussed for a Q-type wire in 1 plus 1 dimension. So it becomes some kind of Pfaffian. You have to regularize the Pfaffian by dividing by the Pfaffian with the opposite mass. And then you can use the APS, Attai-Patodi-Zinger theorem, to rewrite the resulting partition function in the following way. So this is a partition function on a three-dimensional manifold M3. Can be written as e to the I Chern-Simons gravitational, which depends on the metric, and this Chern-Simons gravitational is 2 pi over 16 . Is this, where M4 is chosen in such a way that M3 is its boundary. Loosely speaking, this is a total derivative that is for kind of small for metrics with very which are close to flat metric. This is total derivative, and you get something like trace. You can rewrite this as integral over the boundary of trace omega d omega plus 2/3 omega cubed, where omega is the spin connection. But for metrics, for non-trivial for metrics with non-trivial topology, you cannot rewrite this as some. This is first of all not gauge invariant, not locally gauge invariant, and more generally you cannot. For metrics with non-trivial topology, you cannot. The way you make sense of this is to write this. And this turns out to be independent of the manifold M4 that you choose as an extension of your M3. And the reason is that this the reason is that this -1 over 24 pi squared trace R wedge R is the signature of the manifold for closed M4. So if you choose a different M4, then the difference in this integral is many of you probably have seen this picture. The difference in the integral can be thought of as an integral on a closed manifold. And this integral on a closed manifold is the signature. So this phase changes by 2 pi over 16 times sigma.
So can you repeat where the gravitational channel came from?
Where this term came from?
Yes.
The way I derived, I started with this action for a massive Majorana. I computed the partition function, which is some Pfaffen. Then that Pfaffen can be expressed in terms of the eta spectral asymmetry of the Dirac operator. The eta spectral asymmetry of the Dirac operator using the Ataya-Kotodé-Zinger theorem can be rewritten in this form. Now the signature, well, first of all, it's an integer. But turns out that because we are dealing with fermions, we have to do this extension preserving the spin structure. And turns out that for smooth spin manifolds, closed spin manifolds, this signature is a multiple of 16. Smooth spin. So this gravitational Chern-Simons term is well defined, and this is an invertible phase in 2 plus 1 dimension whose partition function depends on the metric.
Sorry, I thought isn't the Chern-Simons function invariant under continuous affirmation of the spin connection with the metric?
No.
No?
This is there is an explicit term on M3, right? Let's say take omega to be small. So metric close to the flat metric. This is non-zero. This integral is non-zero. It's like the Chern-Simons term for ordinary gauge field. ADA is non-zero for topologically trivial, for general connections on topologically trivial bundles. Yes?
So sorry, is the following a correct statement that if you want invertible TQFTs that don't depend on the metric, then you only have to consider the torsion part? And then what's the Bordism group in 2 plus 1D for fermions? Like where does Z come from, I guess?
So this is not, so the Z comes from the Bordism group in 1 higher dimension.
Okay.
Right? So we see that this quantization of the Chern-Simons level comes from the quantization of the signature in 1 higher dimension, in 4 dimension. And the signature is a 4D Bordism invariant. Omega 4 spin is equal to Z. So if you want to include these phases, these invertible phases that respond non-trivially to the metric, and in the case when you enrich with symmetry, also respond non-trivially, that depend non-trivially on the connection, what Fried and Hopkins argue is that invertible phases in the dimensions is equal to torsion of omega d plus free part of omega d plus 1. Now this free part always just gives you Chern-Simons terms. So this free part is in some sense easier to understand. It's this torsion part which is the tricky part. Okay, I think this is a good point.
In this context of what is an invariant, is there a distinction between topological versus smooth manifold?
I don't know. But I know that actually signature of a topological spin manifold only has to be a multiple of 8. So somehow but we know that the gravitational, right? But we know that the quantization is given by the quantization implied by Fordism of smooth spin manifold. So that's kind of
okay, if there are no questions, then let's have coffee.